Welcome back to Forge College, everyone. In our last lesson, Introduction to Inheritance and Solidity, we tackled the pure theory behind how inheritance actually works. But today, in this explainer, we're going to roll up our sleeves and draft what I like to call an inventor's blueprint. We'll literally write out a base contract and then pass it down to a derived contract that's totally eager to shake things up. It's going to be a lot of fun. Let's dive right in.
Right, so here is our blueprint for today. We'll start with code inheritance basics, move into crafting the base contract blueprint, and then forging the derived contract. After that, we'll hit the virtual and override keywords, do some quality assurance and testing your smart contracts, and finish up with a recap and next steps. Boom, let's go.
Section 1, Code Inheritance Basics, the is-a relationship.
Okay, the absolute crucial takeaway here is that our new derived contract is a version of its parent. It's not just, borrowing a wrench from the neighbor, it inherits the entire house. When a derived contract inherits from a base contract, it gets direct, built-in access to the parent's state variables, its functions, and its constructors, unless, of course, we specifically lock the doors using visibility rules, which we'll get to in a second. But this structural bond is huge. It literally saves us from writing the exact same code twice. And in Web3, less code means saving time, saving gas, and definitely saving money.
Moving on to Section 2, the Base Contract Blueprint, crafting BaseStorage.
So when we're creating our base blueprint, we really have to decide who gets to see what. We use the internal visibility modifier to keep our family secrets completely safe from outsiders, while still letting our direct heirs, our derived contracts, actually access the data. On the flip side, public means exactly what it sounds like. The front door is wide open. Both external callers on the blockchain and our inheritors can interact with it. Making these visibility choices deliberately, that is step 1 of solid contract engineering.
To kick things off, we initialize this internal state variable we're calling storedValue, and we use a constructor to do it. This constructor is basically the foundational setup for our entire invention. Notice how it takes an initial value as an argument right when the contract is deployed. Because storedValue is marked internal, it is safely tucked away inside our family tree. It's totally invisible to the rest of the blockchain, but 100% accessible to any child contract we decide to forge next.
Speaking of which, Section 3, Forging the Derived Contract. Introducing DerivedStorage.
So how do we legally link our child contract to the parent's patent? It's incredibly simple. We just use the is keyword right up there in the contract header. By writing contract DerivedStorage is BaseStorage, the Solidity compiler instantly knows that DerivedStorage inherits all the non-private traits and functions of BaseStorage. Just a tiny 2-letter word, and bam, the inheritance bond is securely forged.
Now, this brings us to constructor chaining. Remember how our base contract needed an initial value to set itself up? Well, the derived contract has to be the one to provide that. By throwing BaseStorage initial into the derived contract's constructor header, we're essentially taking the required instruction manual from the parent and passing it right into the child's hands. When you deploy the derived contract, it automatically hands that initial number straight up the chain to assemble the base contract first.
All right, Section 4, Virtual and Override Keywords. The modification.
Here is where things get a little spicy, and we need some explicit signals. The base contract uses the keyword virtual on a function to politely leave room for future upgrades. It's basically the parent saying, look, here's how I do it, but hey, you're allowed to change this if you really want to. The child contract, on the other hand, slaps the keyword override on that exact same function to proudly declare I am actively changing this family blueprint. You absolutely have to use both of these keywords. If you don't, the Solidity compiler is going to throw a fit and stop you dead in your tracks.
And here is that custom turbocharger in action. The derived contract overrides the set function. It intercepts the incoming value, adds a massive turbo boost of 10 to it, and then, instead of completely rewriting the storage logic, it uses a fully qualified parent call. It calls BaseStorage.set. This pattern is just brilliant. It lets the child inject its own custom logic, but still heavily rely on the parent's original battle-tested code to actually store the data.
You know what's really cool here? It's how the child contract can directly read and multiply that internal base state we locked down earlier. The derived contract doesn't even need to call a getter function. It literally just grabs stored value directly, multiplies it by 2, and returns it. This perfectly shows why we used internal instead of private back on the base blueprint. The child gets full, unrestricted backstage access to the family data.
Section 5. Testing your smart contracts. Quality assurance.
Okay, every good mad scientist needs to test their invention in the lab. Let's run the numbers.
We've got our BaseSu, we've got our override, we've got our constructor chain. Let's look at the step-by-step schematic to prove this family heirloom actually works. First, we deploy the derived contract with an initial value of 5. Call and get returns 5. Awesome, our constructor chaining worked flawlessly. Next, we call our overridden set function with the number 20. Now, behind the scenes, the child adds its turbo boost of 10, pushing it to 30, and then passes it up to the BaseSu. So when we call get again, it returns 30. Finally, we hit our custom getDoubled function, which grabs that 30, multiplies it by 2, and spits out 60. The math is perfect, and our inheritance wiring is absolutely rock solid.
Section 6. Recap and next steps.
Let's just take a quick step back and admire the beautifully engineered pattern diagram we've just drafted together. We took all that abstract theory and turned it into real, deployable Solidity code. So here are your 3 golden takeaways for wiring up modular smart contracts without breaking the compiler. Number 1, use internal visibility to securely share state variables with your heirs. Number 2, always forward your initialization arguments using constructor chaining right in the derived contract's header. And number 3, use those virtual and override keywords to explicitly manage how functions are modified down your family tree. If you master these 3 tools, you're going to have incredible power to build highly efficient, reusable code.
But hang on, what if our derived contract is, well, a bit more complicated? What happens when your smart contract inherits from not just one, but multiple parent contracts at the exact same time? To find out how to use the super keyword to navigate the absolute chaos of multiple inheritance, you will definitely want to check out our next lesson. Until then, make sure to visit forge.college for more Web3-related explainer content created by Forge College. Thanks so much for joining me today, and happy coding!